Hello everyone, my name is Pegah Nikbakht Bideh. I'm a PhD student at Lund University, and I'm going to present our work today, Flowrider, which is fast on-demand key provisioning for cloud networks. Before describing Flowrider, first I would like to introduce the background on cloud computing and SDN, or software-defined networking. As we know, cloud computing has gained lots of attention in recent years, and notable trends in cloud computing are the use of resource description templates, emergence of serverless computing, and fine-grained resource billing. Resource description templates allow to dynamically deploy workloads and provision them with cryptographic material. Serverless computing differs the operation of the server platform to a cloud provider, and this allows the developers to focus on their application code. With the fine-grained resource billing, the cloud users are billed only for the number of consumed resources. SDN is defined as the separation of control plane and data plane. It helps in network configuration and management, the distribution of cryptographic material to the endpoints with the use of a central controller. With the emergence of SDN, other network operation security did not keep up with the new capabilities enabled by SDN, and the public key cryptography rather than symmetric key cryptography remains the tool of the choice for enabling secure network traffic in virtualized environment. Public key cryptography has some problems, such as the complexity of key management. It's CPU expensive, it can cause additional financial costs, and also in virtualized environment, because the tenants share the same entropy, it can cause the lack of computational capacity. So the alternative solution is the use of symmetric keys. Symmetric keys requires less computational power, and it has firmware support on many platforms. But it has also some challenges, such as key provisioning and key authentication is much more difficult in symmetric keys. Now the question is that can SDN model be used to provision symmetric keys and reduce computational resource consumption? The answer is yes, it's possible with the Flowrider, which I'm going to explain it in this presentation. Before describing Flowrider, I would like to talk a little bit more about deployment in virtualized environment and SDN components. In modern distributed systems, workloads are commonly deployed using a resource orchestration system such as Kubernetes or Mikado. But what is an orchestrator? An orchestrator creates and configures workload environments such as virtual machines or containers. It also deploys network components such as the network controller or network functions, and it maintains a control channel to patch and update workloads, reprovision them with cryptographic material, and collect operational log. SDN emerged in response to the increasing complexity of network deployment, and it facilitates operation and management of virtualized networks. It has several components. The first one is data plane. It contains hardware and software routing components. It implements routing policies that satisfy network administrator goals. Here in this picture, you can see SDN components. I talked about data plane. The next one is southbound API. It's a set of instructions implemented by the data plane, and it allows a two-way communication between data plane and control plane. Control plane is an abstraction layer transforming high-level network operator goals into discrete routing policies based on a global network view. The last component that exists in application plane are network functions or applications. They are used by network administrator to express their network configuration goals using a set of high-level commands. Examples of such applications are firewalls or intrusion detection systems. In this work, we use a custom network function. to generate symmetric keys for establishing secure channels between endpoints, which is Flowrider. Before describing Flowrider, I would like to describe a network scenario that I will use it in describing Flowrider. In this scenario, we have an orchestration node located on a network controller and deploys the two endpoints, client and the server, as well as the open flow switch on the communication path between client and the server. The orchestrator also configures the network controller to establish and manage the network flows between the endpoints and maintains a secure channel with them. We have an assumption here, and our assumption is that the network controller established at the deployment time 3 secure channels based on TLS or DTLS with the endpoints, with client, server, and the switch. And here you can see these secure channels in this figure. So in the network scenario, the client intends to securely communicate with the server. Typical approaches for that are based on symmetric key or asymmetric key material. Each of these solutions have their own limitations. For example, if client and server use multiple network flows, communication on each flow occur over secure channels created with the same pairwise set of key material. And compromising a single set of key material can endanger the security of all flows. And also I talk about asymmetric key material problems, that it requires computationally and resource demanding operations. And also in symmetric keys that provisioning and key management is much more difficult. So the alternative solution is the use of Flowrider. With Flowrider, we can provide per flow key material where a single key compromise does not affect the security of other flows. And also, Flowrider can distribute symmetric key material in a fast, dynamic, and automatic way. And this approach does not require a prior knowledge of the network topology and communication patterns among the endpoints. It also facilitates a centralized maintenance of software or hardware for cryptographic operations. And as a result, with Flowrider, we can have flow-specific symmetric keys. And key provisioning is done at flow installation time whenever the client initiates a new communication with the server. Each time the client initiates a session with the server and triggers the establishment of a new network flow, the controller generates new symmetric pre-shared key associated to that flow and provisions it to both endpoints. Here I would like to explain a run-through of Flowrider. You should remember the network scenario that I explained earlier. We had client, server, the network controller, and the switch. So in first step, the client sends the first packet P address to server. The packet reaches the switch. In next step, or step 2, the switch does not find in its flow table a flow rule matching with this packet. So in next step, or step 3, the switch sends a control message to the controller and requests for more information. In next step, or step 4, the controller generates a flow rule to handle this traffic between client and the server, and it also generates a cryptographic symmetric key, which is called the K, associated to flow F together with a related key identifier. In next step, or step 5, the controller provisions the key K and the related key identifier to both client and server through pre-established secure channels. The controller may additionally provide the client with the IP address of the server. In next step, or step 6, client and server install the received key and related key identifier. If the message from the controller contains an IP address, the client verifies the IP address of the server as well. This can prevent IP spoofing attack. In next step, or step 7, the network controller communicates to the switch the new flow rule F. And in next step, or step 8, the switch forwards the packet to the server according to the new flow rule. And finally, in last step, client and server use the key to establish a secure channel and finally exchange secure data. Now I would like to discuss a little bit more about the Flowrider. With Flowrider, we can generate and provision symmetric keys on a per flow basis between two peer endpoints. And as we know, different flows are related to different and independent security domains. And compromising the symmetric key associated to one flow does not endanger the security of any other flows. It reduces the computational efforts and also reduces the entropy requirements on network endpoints. It's easily deployable with both TLS and DTLS versions 1.2 and 1.3. And whenever a controller determines that one peer was compromised, the controller revokes each per flow key issued to the peer, which is not yet expired, and notifies other peers that the key has been compromised. As I mentioned, Flowrider is compatible with TLS and DTLS, both versions 1.2 and 1.3. So how it's compatible with the first DTLS or TLS 1.2? At step 1, the client sends the first packet to the server, and if we have TLS handshake, this first packet is a TCP SYN. If we have DTLS handshake, this first packet is a client hello handshake message, and in either case, C performs the DTLS handshake in pre-shared key mode. And finally, in step 9, which was almost the last step, the client points to the server the key, which is going to be used as a pre-shared key for mutual authentication. But how Flowrider is compatible with TLS or DTLS version 1.3? For version 1.3, the client has to include in the client hello handshake message the following information: the PSK key exchange mode client hello extension, and also a pre-shared key client hello extension, which present at the last extension and include a collection of offered pre-shared keys. This collection is structured as a list of key identifiers and a list of key binders. Now I would like to talk about our experimental evaluation and our results. In our experiments, we have used the TLS 1.3 with the GNU TLS library. We have 4 Docker containers. Client and server implementations were created for using symmetric keys and certificates, respectively. We have another container, the controller container, that runs Ryu instance version 3.12, and the custom Python application, which was the Flowrider application that defines packet to be matched and subsequently generates and delivers keys to the endpoints. And we have also the OVS container, an instance of Open vSwitch that routes packets between endpoints and forwards predefined packets types to the controller. And here you can see the results of our tests. In our experiments, we ran the TLS handshake in both PKI mode with PKI certificates and also in PSK mode with the use of Flowrider scenario. In our tests, the client established a TLS session with the server in the considered mode and terminated the session immediately afterward. We ran the tests 10,000 times in both cases And in each case, the OVS or Open vSwitch flow table did not contain any flows between the client and the server. As a result, the first packet was always forwarded to the controller. And in our experiments, we have measured task clock, CPU utilization, and also the total time elapsed for the handshake. And here you can see the minimum, maximum, mean, median, and other values. And as you can see, the mean of the task clock is lower for Flowrider in PSG mode, which is 3.37, and in PKI mode, it's 14.31. The CPU utilization is also much less with Flowrider scenario, but the total time elapsed is larger for PSG mode. And this is partly due to the overhead introduced by the communication between the switch and the controller. However, this overhead is mostly offset by distributing the pre-shared keys after the first TCP packet and before the TLS negotiation starts. And finally, our conclusions. Flowrider is a novel approach to distribute cryptographic symmetric keys to endpoints in software network. With Flowrider, we can provision symmetric key material, and it significantly reduces the number of CPU cycles needed to establish a secure communication channel. And it makes key distribution agnostic to the network topology or the communication patterns between the endpoints. And as I mentioned, it's compatible with TLS 1.2 and 1.3 and also DTLS, both versions. Thank you for your attention.